So what I'd like to document here is basically what I've done is increased our operating current by adjusting our constant current source. I'm still using this 1.5 k ohm cathode resistor, but my bias voltage is now 27 volts. So that's 18 milliamps now of current. As I mentioned before, because we have the same 1.5 k ohm resistor, by increasing the current and by increasing the bias voltage, I'm shifting my operating point to the left. And so I'm going to get less and less symmetrical swing capability as I increase the current for my given cathode resistor. But what I wanted to show here is the trend I'm seeing, where if I run the THD versus output profile, the THD seems to continually improve as I increase my operating current. So I'll run the THD profile. And those little hiccups there are the auto scaling of the AP, so those aren't real artifacts. But you can see up in this range, I start to get THD improvement with a small increase in current. Very little change in headroom, but it starts to roll over maybe a little bit sooner. Again, just due to the shifting of the operating point. So what I'd like to do is come back and test this and move to my second proposed operating point, which would be, again, 20 milliamps, but now use a 1.2 k ohm resistor to recenter and get everything back on center for maximum signal swing. And what I expect is the performance to continue to improve as I increase the current. And that's going to be ultimately sort of a design decision in terms of allowable driver THD versus really the lifespan of the tube, because as I increase the current, I'm dissipating more power in the vacuum tube. I'll also caveat this now that this THD may not be representative. The AP is representing a pretty, as we've discussed before, capacitive load, and is capacitively loading the voltage divider too. So first of all, the bandwidth that we measure with the AP using this voltage divider scenario shown here is not going to be representative at all. This is gonna start basically attenuating our voltage division effect due to the capacitance of the AP. So we can't assess the bandwidth on the AP, actually, and I can't assess it on a digital multimeter, and I'll do that in a minute. But the AP does give us these headroom numbers and can give us an idea on trends. And so in either case, honestly, though, the THD performance is still quite good. I mean, if you figure this is 215 volts, so 430 volts peak to peak of signal swing out there. I mean, this is pretty damn good. But as always, we'd like to improve this as much as we can. And like I said, we shouldn't pay too much attention on these absolute THD numbers, because the other thing to keep in mind is we'll get some additional distortion cancellation once we add the driver, and even further distortion cancellation with the 845s, because the 845s, as in conjunction with this gain stage, are going to provide some distortion cancellation, and we may see these numbers improve significantly. So there's a few factors why we can't completely believe these THD numbers, but like I said, I would like to continue to try to increase the current while balancing the voltage swing to see if these numbers, how much these numbers can improve as we increase to closer to 20 milliamp operating point. Here I want to check and verify that our AP voltage calculation is indeed correct. And so I'll run an example. Right now the AP is connected. We've got 100 millivolt input signal, and we have 1.173 volts output. So 1.173 times 11.806, we should be getting 13.84 volts RMS output. What I've also connected to this node here is our 10 mega ohm DMM. And so our AP and our digital multimeter should agree at roughly 1.173 volts. If I go down to our digital multimeter, you can see it there, 1.18 volts. So they agree with each other. Now watch what happens if I disconnect the audio precision as a load. We get 1.39 volts. 1.39 volts times 10 should be 13.9 volts. 13.84 is what we calculated. So the AP is indeed presenting approximately a 10 mega ohm load. And our digital multimeter, because it represents a 10 mega ohm load, if we disconnect the AP and just measure with the DMM, we get our true 10-to-1 divider. So that number multiplied by 10 is now the true output voltage. If I reconnect the AP, you can see the AP is loading down the output and our voltage divider by that amount. The one thing we can also do is spot check the bandwidth using our digital multimeter. So back to our 0.1 or 100 millivolt input signal, here's our output signal. If I use that as a reference for what's called DBR, DB reference, and I relate my measured signal on the AP relative to that, we should get 0 dBr. So let's see what our dB roll-off is then relative to 1 kilohertz. Let's see how that changes at 50 kilohertz. It's pretty bad. You can see the AP says 9.55 dB down at 50 kilohertz. Of course, this actually isn't real, and again, this is where you need to be careful if you're doing this sort of work. You have to think through what loads your equipment represents to the circuit you're trying to measure. So 50 kilohertz is not really 9.55 dBr down. So what I'll do is go back to our digital multimeter. We're at 50 kilohertz, but what I'll do is I'll disconnect the AP from our voltage divider. There you go. You can see how much higher the voltage really is when we present a higher impedance load. So 1.075. If we want to calculate this loss, we'll do 20 log 1.075 divided by, this is what we got at 1 kilohertz, which was 1.173 volts RMS. We're only 0.75 dB down. So again, the load and the reactive loading of the AP really takes its toll and loads this voltage divider. And this is also why we don't want to connect the AP directly to the plate output. Although we'll measure the voltage accurately at 1 kilohertz, it'll load down the stage and it won't give us the correct gain of the stage. It won't give us remotely the correct distortion, because the 100 k ohm load and the capacitance, parallel equivalent capacitance of the audio precision and our cabling will load this down much worse than what our cathode follower driver stage will present to that gain stage. So anyway, just wanted to document that here. And I guess this also highlights why the driver is so important in front of an 845. An 845 is a difficult capacitive load. You'd have all these exact same issues: poor bandwidth, poor linearity, lower than expected voltage gain if we connected this directly to our 845s. And that's why we were not going to do that. We're going to buffer this with a driver, and therefore we can then drive our 845s just like we can then drive our AP accurately. So I'm not going to dwell on getting too many THD or bandwidth measurements out of this stage until we add our driver. Once we add our driver, we can then run the full gamut of AP measurements connected to our driver, because our driver can handle this sort of load just fine. And therefore, we will then know very accurately what the combined performance is of this gain stage plus the driver once we connect our AP to the driver. I hope that makes sense. And like I said, where I wanted to test next was this stage and compare it. What I will compare, I guess, is the THD versus output waveforms at 1 kilohertz. I'll make a comparison across a couple different tubes. So I'll take a weak 6H4 and a strong H4, and I'll plot these curves. And then I'll also do a comparison of my 15 milliamp operating point, as well as a recentered 20 milliamp operating point, and see how the THD versus signal compares. And that should at least give us some relative comparisons that will be useful, and then we can kind of make some decisions on how to adjust the stage now and down the road once we connect the driver. Before we close out this video, and I know this has been one of the longer videos so far in the series, I wanted to show the performance of the amplifier or preamplifier thus far with two different 6AH4s. So the blue curve is 6AH4 1 with a 1.5 k ohm resistor. The orange curve is 6AH4, what I call tube number 2, with the same 1.5 k ohm resistor. And tube number 2 is a stronger performing tube. And you can see that its THD performance remains significantly lower than tube number 1. So that's strictly the tube performance for the same operating condition, which again I guess isn't unexpected because this is an open loop amplifier, and the performance of the amplifier is going to be highly dependent on the performance of each individual vacuum tube. I then went ahead and used those same tubes, and as I discussed previously, I then substituted in our cathode resistor for 1.2 k ohms, and then recentered the bias, which gave me now about a 20 milliamp operating point. So a higher operating point compared to the 1.5 k ohm resistor. And that 20 milliamps gave me a 24 volt bias across this 1.2 k resistor, and was the best or very close to the optimal center operating point for the second operating point. What's interesting and what is sort of unexpected compared to what I saw by just increasing the current with the same cathode resistor, by moving to this lower cathode resistor and then increasing the bias current, my THD performance is actually worse. So blue to gray is the change in operating point on tube number 1, and orange to yellow is the change in operating point on tube number 2. So in both circumstances, or for both vacuum tubes, as we increased our current and recentered the operating point for maximum signal swing, the THD performance is a little bit worse. So I'll spend some time once we get further along and build the driver digging into this, maybe a little bit more onto why that's the case. But I'm wondering, or thinking that maybe it's because the lower degeneration that we have with an unbiased or unbypassed cathode resistor in our 20 milliamp case. I'm wondering if that's what's affecting our performance. In either case, we can see that the stage does perform really well, and our clipping point is greater than 200 volts peak, as we discussed. So this is scaled. I measured with the AP, and then I scaled by our 11.806 number, and then multiply by square root of 2 to turn the RMS that the AP measures into an actual peak number. The peak is what we care about if we want to drive the 845 grids to their maximum. We need to remember 170 volts approximately peak. If I look at that same data set, but instead of using a logarithmic scale, I use a linear scale, we can see how well the stage performs a little bit easier. And so actually I drew a line here at where our 170 volt peak output swing number is. And you can see we actually have approximately 50 volts of headroom to 220 volts peak before any of these operating points or tubes start to clip. So we've got massive headroom. And in fact, this is essentially, it's not quite a 3 dB gain. It's, I think it was a 2.5 dB gain on 170 volts to 220 volts, which actually means, assuming our output stage can handle it, this is essentially would be like a 75% more output power gain if we could get this voltage effectively onto our output tubes. So this stage does really well, and where our typical or our estimated operating point is going to be far away from that clipping region. So it's doing really well. And real quick before we close, here are the two curves I got from the curve tracer of the two GE 6AH4 tubes. So tube number 1, you can see from the curves, is significantly weaker than tube number 2. Both function fine and both offer nearly the same headroom, but the distortion performance is clearly superior on tube number 2. And that seemed to follow. I did quickly spot check a few different vacuum tubes, and that trend seemed to follow. The weaker tubes seemed to have a little bit more THD, and the stronger tubes had a little bit less THD. As I've said before, I'll caveat that with this is measured with the AP, which may not be representative once we add our driver, and especially once we add our 844 output stage. We'll likely have more distortion cancellation because of the phase inversion as we're cascading these stages, and the impedance that the AP presents on these tubes is not going to be representative of a cathode follower, which will be represent a much higher load impedance for this gain stage. So we'll see how that performs and really continue to build out this preamplifier before we can fully evaluate the entire preamplifier performance. But so far, for our design goals, we're doing really well, and I'm very happy with this stage. Thanks for watching, and take care.